So, welcome to the second half of Psych 521, all online. Again, just while I have you here at the start of this slide, I want to appreciate and thank you for any patience that you've shown and consideration. Definitely spend some time on Blackboard, really checking out how to make assignments, how to post assignments, what kind of files you need to use. Try to figure all of that out before a due date comes up. We're going to work as hard as we can to keep this class basically in the exact same structure that it would have been in person, simply online. I feel very strongly that this is a core set of skills that you are learning and a core set of abilities. So the ability to actually understand these statistics but also use them and interpret them, I think, is a very important part of all four programs, skill sets, and therefore I want to make sure that we are keeping the rigor and a level of education the same as much as we can within this online format. If you have any questions, please reach out to either me or David, and we're going to work very hard to make this as seamless as possible. So today we're just reviewing ANOVA and ANCOVA before we move on to more complex uses of these technologies, these techniques. So we're going to talk about between subjects ANOVAs, within subject ANOVAs, factorial ANOVA, and then of course the ANCOVA, which adds a covariate component where we're actually factoring out a factor that we think might be a confound. So we're identifying a confound, and instead of just worrying about it, we're actually measuring it to remove it. So just a review of between subjects ANOVAs. Basically, when we're looking at an ANOVA, we're talking about a one-way ANOVA at this point, which is simply a single variable, and between subjects means that it's a categorical IV, a categorical variable, where each person in each category is only being exposed to one level of that category. So there's a single outcome, and that outcome is the DV is continuous, and there's a single predictor, and it's an independent variable, and it is categorical with 3 or more levels. If there's only 2 levels, there's no reason to run an ANOVA. We could just run a t-test. And again, in statistics, we always want to kind of follow the idea of the simplest solution is always the best. So if there's a statistical technique that is complex versus a statistical technique which is simplistic, even just mathematically, we're always going to use the simpler method if it's appropriate to the data or the question we're asking. There is no limit on the number of levels or categories within that IV. So example, again, generally speaking, what we're talking about is number of conditions, groups, or factor levels, and we usually refer to that as K. So K is the number of groups, factor levels, or conditions within an IV that is categorical within an ANOVA. And again, if it's less than 3, so if you only have 2 levels, just use a t-test. Do recognize that as we add conditions, we are decreasing our degrees of freedom, and we are making it harder to detect an effect. So if we're running a between subjects one-way ANOVA with a IV that has 3 levels, if we added a 4th level, a 5th level, or a 6th level, each one of those increases is also going to reduce our power. So the units in the categories are independent. That means that not only are they different people in each level, group, or condition, but also they are not impacting each other or have a direct effect on each other. So that is, again, kind of the assumption of independence. So let's go through an example. Is there a relationship between state and hospitality? And state here doesn't mean psychological state. I just went for an old-fashioned different states of the union. I don't know if you're picking that up or not, but one of my Great Danes is deciding to bark loudly right now. So we're going to ignore her and continue this lecture. Maybe you can hear her. I'm not sure if the mic's picking her up. So the F ratio in a between subjects ANOVA is the between group variance of the effect size of the difference between the groups. So again, what we're basically having is, just as we've always had, the top of the equation is the actual effect size, the bottom of the equation is all variance. And we're wanting to see, is that effect big enough that it actually is noteworthy over the total variance or just the noise within the sample. So the within group variance is a measure of error or within group variability, in other words, the total variability within the sample. And the mean square is then a measure of the variance. So again, we're going to have our sums of squares between our effect divided by our degrees of freedom between. And again, degrees of freedom between, that's that degrees of freedom that's affected by the number of levels that we have. So the more levels we have, the larger this number. The larger this number, the smaller the effect size is going to be, because the effect size, sum of the squares between, is being divided by that degrees of freedom. Likewise, we want to minimize the total variance in the bottom of the equation, sums of squares within. So the larger our sample, the bigger our degrees of freedom within is going to be, which means since sums of squares within, total variance is divided by degrees of freedom within, sample size, effectively, we're going to get a smaller amount of variance on the bottom of the equation with a larger group of people. And again, mean squared between is simply the sums of squares between divided by degrees of freedom between. Mean squares within, the bottom of the equation, is sums of squares within divided by degrees of freedom within, and that is where we get our F, our calculated statistic. So, is there a relationship between U.S. state, Georgia, Illinois, New Jersey, and South Carolina in hospitality? We run our statistics. We get a sums of squares between of 180. So again, that is effect variance. Our degrees of freedom is k minus 1. So we have 4 conditions. Minus 1 is 3. Degrees of freedom is 3. So 180 divided by 3 is a mean square of 60. Our sums of squares within, total variance, is 300. Our degrees of freedom here is 20, so that also tells us a little bit about our effect size, our sample size. And again, the larger that sample size, the smaller the number on the bottom of the equation would be. In this case, 300 divided by 20 means mean squares of 15. 60 divided by 15 is an F of 4. So we check to see if an F of 4 with this degrees of freedom, 3/20, would actually equate to what we want. In other words, is it significant? And we find out indeed it is. So our F 3,20 equals 4 with a P less than 0.05. What we don't know is which states are more hospitable. All the F test tells us is that there is an overall or omnibus difference somewhere in our conditions. Having found a significance, we now have to do post hoc testing. So post hoc tests determine which groups are different from each other, and we only conduct post hoc tests if we have a significant F to begin with. They're typically paired comparisons that are made or designed not to inflate type 1 error. In other words, having found an overall omnibus test that has not been inflated for type 1 error, we're now wanting to go in and look at individual comparisons. So the types of post hoc tests include Sheffey. Sheffey's test is actually a series of ANOVAs comparing 2 groups at a time. It is overly conservative. So generally speaking, if you run a Sheffey's test and you do find group differences, that's good. That means that not only are they there, you're more confident that they are there. However, there may be some times where you get an overall F test and Sheffey comes back and says there are no group differences. The most common used is Tukey's honestly significant difference test. It is adjusted again to not inflate type 1 error, though it is a little less stringent than Sheffey's. It's based on mean differences. However, it is somewhat limited to groups with equal or near equal sample size. So sometimes there's a limit there. The greater the difference between the number of people in each of our levels or conditions, the less likely Tukey's HSD test is the appropriate test. However, generally speaking, through random assignment, we usually have equal or near equal group sizes when we're doing an ANOVA one way with a single categorical variable, and therefore this is probably going to be the most used test. There's Newman-Cools. Basically, again, these are all just different versions of ways to look at it. The advantage here is that it is a little less stringent than Tukey's HSD, and it does not have that limitation that the groups need to be near equal sample size. So if you have a sample where you have a large difference in the number of people in each condition, and you're not wanting to necessarily have a very stringent test like Sheffey's, you could use Newman-Cools. And finally, there's LSD. It does not control for type 1 error. It is likely to find differences no matter what. And in fact, you can have a non-significant F test. In other words, the F test says there's nothing going on, and LSD will still find group differences. Why do we use this still occasionally? Well, if we do have a significant F, in other words, the F tells us it's time to go look for post hoc tests, and when we use either Tukey's or Newman-Cools or Sheffey's, we find no differences, then you might be able to make an argument of using LSD, a less stringent test that's more likely to find differences, because you were told by your omnibus test, the F test, that there should be differences to be found. So just looking at Tukey's HSD, the way Tukey's HSD is, it creates an honestly significant difference value, a Q. And Q in this case, if we actually ran the equation, would be 2.71. And what that tells us is we can simply look at all the mean differences, looking for any mean differences that are greater than 2.71. If so, those are our significant differences. So looking at the chart here, we just take a look at Georgia, Illinois, New Jersey, and South Carolina, and we get the mean. So the mean of Georgia is 7, the mean of Illinois was 5, the mean of New Jersey 4, and the mean of South Carolina is 6. We compare these to each other. So for example, the difference between Georgia and Illinois is 2, the difference between Georgia and New Jersey is 3, and the difference between Georgia and South Carolina is 1. And we just simply do this for all possible combinations. So the purple numbers represent the actual mean differences. Now the Q here is 2.71, so only a difference greater than 2.71 is significant. So even though there was a significant F-test, what we find is there really is only one difference that is meaningful, and that is the difference between hospitality in Georgia, very high, and hospitality in New Jersey, relatively low.